1952 respectively. After his PhD, he was in IIT Kharagpur as a senior research fellow for 6 months. Then he has joined Tata Auxiliary Transportation Unit, India as hardware specialist. Currently, he is working as a senior power electronics engineer at Hawaii Technology in Sweden. He has authored and co-authored in various research papers in international journals and conferences, which including some renowned IEEE transaction. His paper awarded as the best paper in IEEE Second International Conference on Sustainable Energy and Future Electric Transportation in 2022. Also, he has authored in different Indian patents. Most of them are already granted. Dr. Das has research experience in the area of power electronics and has industrial experience as an R&D engineer as product development. His research interests include DC-DC converter design, multi-level inverter, renewable energy harvesting system, charge for electric vehicles, EV application, EMI, and EC digital embedded control, PCB design, nonlinear control of switch mode power supply, SMPS. With this, I request our expert Dr. Dhiman Das sir to kindly enlighten us with word of wisdom. Sir, please.
Thank you, Ms. Khushbu. Thank you for introducing me. That was Tata LXI, and my present company is Huawei Technology. Huawei Technology is a Chinese name. It's difficult to pronounce. Yep. Okay, so should I share the screen? Hi, I'm Dhiman Das. Good evening all. So today we are going to discuss some soft switching technique of power converter. So okay, so let's start with some briefly basic switches, which is presently silicon MOSFET, silicon IGBT, and silicon carbide MOSFET. So silicon MOSFET is rated up to 650 volt, and it is widely used as the cost is low. For cost optimization, silicon MOSFET is still used in the most of the product, and it is very much popular device in power converter, switch mode power converter. So it is rated up to the maximum voltage rating is 650 volt. The 650 volt it can withstand at block, or you can say it can block up to 650 volt. And if you want to block more than 650 volt, so we can go for IGBT. But the problem is that the switching frequency of IGBT is limited to 20 kilohertz. But this device is available around 1200 volt level. So now for high-speed switching, silicon carbide MOSFET is used, which is available in more than 650 volt. Also, it can operate at high speed, so more than 50 kilohertz, around 100 kilohertz, 150, depending on the design. So it can be used at high power as well as high voltage level also. So there are some basic difference between silicon and silicon carbide, silicon MOSFET and silicon carbide MOSFET. So basically, if you consider in terms of voltage level, which is the first design criteria of selecting switch, how much voltage it can block, or the reverse voltage. So for silicon, it's 650. For silicon carbide, 1200, 1900 volt, 1000 volt, 1 kV, 1.2 kV, is standard. So in special case, 1.7 kV device is also available. So if you go internally, internal physics of the device, so it has the very high band gap energy. That is why, and in a same package or in a same device case, we can go for more higher voltage because of this high band gap energy, and the critical breakdown voltage is also high. So the saturation voltage is also high, and the mobility factor is also low. That is why it can operate at a very high switching frequency, and low RDS on, and low switching losses and all these things. So the thermal conductivity is also high, so it can evacuate the heat very much quickly. So affect so the need of heat sink is sorry, anybody want to ask anything? Hello.
No question, sir.
Oh. So the requirement of heatsink is very low in this case. Now, if we go for the gate driver, there are various kind of gate driver available. So I am just briefly go through some different kind of gate drivers. First of all, it's completely depend on the application. So there could be two scenario. One is non-isolated and another is isolated converter. So for non-isolated, there could be three scenario. One is high side switching like buck converter, low side switching like boost converter. High side switching means the MOSFET or the switch is tied to which bus. If it is tied to the supply bus, that is called high side switch, and if it tied to ground bus, then it's called a low side switching, like boost converter. In boost converter, switch is tied to the ground bus. One end of the switch source is tied to ground. Now, in some cases, the which is a half bridge configuration, where both switches are required, where one switch is tied to high, another in the same bridge or in the same leg, another switch is tied to low side. So this configuration is called half bridge configuration or bridge configuration. For isolated converter, we need optical isolation, which is commonly used, but it is very slow and very for high frequency operation. Optical gate driver you cannot use because of the propagation delay. Next comes flux couple. It's a kind of high frequency transformer kind of thing. Another is capacitive isolation, that is called CMOS isolation. Another is RF isolation, which is inside gate driver. There is some flux, some RF modulation, so that the primary and the secondary side get coupled. Okay, so now say this is a gate driver IC. So output of the gate driver is directly connected to the gate, and this ground pin of the output buffer is connected to the source. They are connected to an resistance, which limit the current to charge the GS of the gate to source capacitance. So if you go for same resistance, then your source current and the sink current will be the same. That means your timing means charging time and discharging time will be the same, because your path of conduction, that is RG, is always the same. So now if you do so for a full bridge, for a half bridge kind of MOSFET, for a half bridge kind of configuration, when your upper switch want to get high, so as simultaneously your lower switch current need to be reduced from certain value to 0. So if you drive with the same current, so the intersection of these two current profile, the intersection junction is when your both switches are simultaneously on. So that is the called the shoot through current. So the intersection current or the shoot through current will be high. Now instead of that, if you fast turn off the switch and slowly turn on the switch, say slowly turn on the high, so from 0 to certain value, or the load current from a switch, from a high side switch, is if you slow it down through RH by increasing RH, then it will go slowly. Now if there is this scheme is called steering control, or steering the current. So if you control the discharge current through this diode, this is steering circuit. Now, so if you reduce the RL very much compared to RH, means high resistance, so it will follow the current will follow the least path, which is RL. The diode will conduct, this D will conduct. Now the fall of the current will be very fast. Now if you can see that when it is happening, so the intersection area is very small, so the shoot through current is very small. So this is the technique to maintain the shoot through, to optimize the shoot through current and optimize the bridge. Now this is an experimental waveform when how the timing control, what is the effect of this timing control. So this is the VDS, or drain to source voltage, which is also, you can say, the switching stress or voltage stress across the device. So when you drive the gate with 1 ohm resistance, you can see it can rise up very fast, but you can see there is too much oscillation, because when you charge the gate capacitance very much quickly, then the MOSFET is turned on. As a result, the current try to flow. So DIDT, the rate of change of current, is very high through the switch. Now when DI is very high, also DT is very small. DT is in the denominator side. So if DT is small, so overall DIDT factor is very high. So now this DIDT factor is multiplied by the parasitic inductance. So LDIDT is cause this kind of oscillation. Now if you can see, if I slow down the current, charging current of the gate with 15 ohm, so you can see the gate slowly will charge very slowly. Also this oscillation is quite damp in nature. So if this LDIDT is added, yes. So this DIDT is based on this parasitic. There is a lot of parasitic inductance. So this DIDT is added with the with this bus voltage. So if you solve the KVL, so you can end up with bus voltage plus LDIDT. So now bus voltage is fixed. You cannot change the bus voltage. Now if this LDIDT, which is inductive kickback, if this inductive kickback voltage rise too much, and if it hit the limit of the voltage rating of the MOSFET, which is 650 volt. So what will happen at that point of time? The drain to source layer or will get breakdown. That is called avalanche breakdown. So drain to source layer will be avalanche breakdown. There is now when this avalanche breakdown happen, it is not a recoverable. It's no longer recoverable. If it is a Jenner breakdown, it can be recoverable, but when it's avalanche breakdown cannot be recoverable. As a result, drain and source will be shorted. Now, in a leg, when drain and source, one drain and source is shorted, another, when you turn on the another switch, so whole bus will get shorted. Now, when whole bus will get shorted, immediately a huge through current will flow through the switch. Now, now there will be a fuse protection also. When fuse try to melt, before that, when fusing action takes place, before that, because of this high current, the bond, there is bond wire and the lead resistance that will first blow up, or it will melt it completely. So the timing control is very much important for your design of power converter, and this is the basic of driving switch. You need to have the the timing control of the gate, otherwise your converter will blow up. Okay, so there is one another concept is called Miller compensation or Miller effect. Now, when you turn on the switch, the voltage across the switch is 0, and ID current or the drain current is flowing through the switch. Now, when you turn off the switch, the drain current will try to flow, because as it is a practical scenario, so drain current will not immediately stop from a certain value to 0. The rate of change of drain current is, there would be some slope, so that it can follow a slope from a certain value to 0. Now this slope is depend on the inductance. So when drain current try to fall from a certain value to 0, now now there is a yes. So now there is one capacitor branch, which is a parasitic capacitor of a parasitic capacitance of MOSFET. So there is CGT, CGS, and CDS. So this, there is, if you draw this circuit separately, then you can see there is two capacitor branch. One is DS and one is GT plus GS. So now among them, which one is lower, the current will follow that path. Now CGS and CGD is summation of CGS and CGD is lower than CDS. So a small amount of current will try to flow from CGD and CGS. Now when the current try to flow, then the CGS will going to charge slowly. Now when it going to charge, and when the voltage across the GS cross the threshold voltage of the MOSFET, which is approximately 2 to 5 volt, around 2 to 5 volt, depend on the MOSFET, but in the range of 2 to 5 volt. So when it reach to 5 volt or or you may say generally in threshold voltage, then immediately the MOSFET is try to turn on again. So this is called a false turn on. Actually, you are giving a off pulse from your controller to the gate driver, but because of the Miller effect, it again turn on. And in this oscillation, when it is turned on, but it cannot sustain the state, because actually you are issuing the gate pulse to turn off, and this current is very small. So again it will get turn off. So again it will turn on. So this kind of oscillation will happen if you do the experiment. Have you ever see on the experiment this kind of phenomena happens quite. So, and especially when your drain current is very high. So to recover this, there is one concept called Miller clamping. So we use a linear MOSFET or high speed smaller MOSFET and use a comparator to sense the voltage across the gate. And when it reaches some value, say 2 volt or VTH, say threshold voltage of the MOSFET, then immediately the small MOSFET will turn on, so that the gate capacitance directly shorted through this internal switch instead of getting charged. So this is very much important feature of choosing a gate driver or of a gate driver. So when you design a complete gate driver, so we started with 2 line only, output and ground line. So you can see there is actually 4 lines. One is high source current, sink current, and is a clamp current or clamp voltage, clamp pin. So actually you need 4 wire or 4 pin along with the ground of both to drive a gate properly. So there is a lot of if you see the real circuit, if you see inside the MOSFET, there is actually the MOSFET is the wafer of the MOSFET. If you remove the plastic package, the black package, there is one wafer of MOSFET. Now this wafer is actually connected through bond wire with source and gate, and this wafer or the substrate is called substrate, to be precisely. This substrate or this is actually placed in the drain pin, which is also connected to the tab of the MOSFET for heat distribution. So now if you see the complete scenario of a, this is the bus. Now you cannot connect the bus directly to the pin of the MOSFET. You have to place a wire. You cannot connect a source directly to the MOSFET. You have to use some wire or PCB or connector, whatever. So bus is a far distance from the bridge actually. So now that distance is a copper distance or anything. The distance connected through copper. So now this copper have a finite length or a finite amount of material. So that material, when current try to flow, that material is behave like an inductance, because after all it is an conductive material, and when
Super. Enache.
Uh, if you have any question.
Hello. Sorry, sir. Actually, someone
No problem.
mistakenly
No problem. No problem.
his or her microphone.
No problem. It's okay. Um, so that amount of copper or conductor have some when current is flow, it create an inductance. This is called bus inductance. And when you connect the two MOSFET, there is one trace inductance, because you are connecting two MOSFET, source and drain of the MOSFET, which is called midpoint or the pole. You have to connect through a PCB or anywhere or any kind of pin or any kind of conductor. So that also create a trace inductance. Now from the substrate to the pin, there is also a bond wire. That bond wire also cause a bond wire inductance. So if you, all these are parasitic inductance. Now all these inductance create this oscillation. When you are turning off the MOSFET, turning on the MOSFET is very easy, but it is difficult when you turn off the MOSFET. When you turn off the MOSFET, all these inductance try to oscillate with the body capacitance of the MOSFET. Now to avoid that, we can use a snubber that is called bus snubber. So across the bus or as close as the possible to the device, you can connect one capacitor. So when the induced current is required or the switching current is required, this capacitor can supply the current, immediate current, and so that pulsed time, during that time the capacitor can discharge, and later when everything is settled down, then the settling current or the maximum current can draw from the bus. That is one method, but you cannot avoid this ringing. Okay, now this snubber capacitor is depend on the load current, how much load you are trying to, how much current you are trying to extract from the midpoint or the pole. Now when you increase the amount of current, so snubber capacitor can discharge quickly, because when you increase the current, this snubber capacitor also have some limitation, has a certain finite value, so it can discharge immediately. Then this bus inductance and all these things come into picture. So overall you cannot eliminate this ringing effect, but you can minimize it, or you can suppress some up to a certain limit, but you cannot eliminate it completely. Okay, so now this all is called hard switching um, scenario. Now what is the remedy for this oscillation? If you go for soft switching, where all the parasitic inductance, you can use all the parasitics to charge the body capacitance of the MOSFET. Then you can use all the parasitic energy to charge the output capacitor of the MOSFET. Then if you turn on, then as you absorb all the energy to the output capacitance, so there is clean waveform, not this kind of ringing. You cannot experience this kind of ringing. That I will discuss later. So all this resonance converter, all this soft switching converter is using this kind of technique. This is widely used in the industry because all of the industrial converter is mostly soft switch. Okay, another is called Kelvin source. Another concept is called Kelvin source MOSFET. So when to eliminate this bond wire, so when you there is a current, so in across the bond wire, the LDIDT L bond wire inductance into DIDT times voltage is appear across the will along with gate driver voltage appear across the gate. Now, if it is cross the limit of the gate signal, then your gate layer can be break or your gate layer can be destroyed. So when it happen, you may encounter that only gate to source will be short circuited. Rest of your MOSFET is okay. Means you can use this MOSFET as you can use the body diode of the MOSFET, but you can not use it as a switching element because your gate is damaged. You can only use as a passive element like diode. Now to eliminate that, there is one concept called Kelvin source MOSFET, which is 4-pin MOSFET instead of 3-pin. We generally know the 3-pin MOSFET, gate, drain, and source, but here the 4th pin is a signal pin, which is just directly connected from the MOSFET, source of the MOSFET. Instead of the instead of the high current path, there is one low current path. That is why this signal source and gate are different from the power source and power drain. Now there are different protection. When what is on-time protection? During on-time, during on-time, these are the short circuit protection. So during on-time, when the pole is short circuited, or our load is short circuited, or anything, any power path got short circuited, then a huge amount of drain current try to flow from the drain, or through the MOSFET. Now to encounter that, to protect that, there is different protection available. So that is DSAT protection. Another is current sensing protection and VDS sensing. Now this completely depending on your application and your cost involvement, this protection can be implemented. First is DSAT protection is very much useful in IGBT, not in case of MOSFET or not in case of SiC MOSFET. So next is a current sensing through shunt. That is also very useful, but when you implement that, the shunt power across the shunt will just get wasted. So to eliminate that, you can use the inherent RDS on or on resistance of the MOSFET, and you can measure the turn on current flowing through the voltage across the MOSFET is just current flow through the MOSFET times I into R. So the times the turn on resistance, that if you can sense that is also give you an idea or an approximate idea that how much current is flowing through the MOSFET. So if you set a threshold that up to this much current, or I can allow to flow from my device. So after that, you can turn off the device when that limit is reached. But the problem is this: your turn on resistance or RDS on and RDS on is completely depend on the temperature. So when temperature varies, this RDN or RDS on is get changed. So that is why using a sensing resistor or shunt resistance is very much useful. But all these things depend on your system design and application. How a designer want to sense, want to optimize the things. Now come to turn off protection. When you turned off the MOSFET, there is only one uh, breakdown possibility is that due to the DIDT ringing. So now to prevent this avalanche breakdown, there is two option: active clamping and advanced active clamping. And when MOSFET is in floating condition during daytime, or when your pulse is off, then a certain leakage current may flow. Then you can sense the gate current, whether it is turned on and the current is flowing or not. But this is very rare case. You can also implement all this protection because of advanced technology like AI and all advanced algorithm. You can implement all this technology, all this protection, and make your system more reliable. So now we can discuss briefly what is DSAT protection. Now DSAT protection is when you turn on actually it is implemented in IGBT. If you see the Skyper 32 block made of semicon, there is they implement this kind of protection in that block IGBT. So when you turn on the IGBT and you want to draw a certain amount of current, then ideally with increase in current, ideally the voltage across the CE or VCE, voltage across the collector to emitter, should be a certain value. But when desaturation happens, when you try to draw a more amount of current, then this operating point of the MOSFET try to shift. That means the voltage is going to rise. Voltage across the MOSFET, voltage across the transistor or the IGBT is going to rise. So then it is no longer in the saturation region. That is why it is called desaturation. Now the possible reason for this desaturation is temperature effect or the short circuit or the overload condition. Now you have to stop the operation of the IGBT, or you have to stop the gate pulse, because you can sense that there is some abnormality happens. So now there is one sensitive DSAT sensing pin voltage across this MOSFET. Across this IGBT you can sense, and there is one RC filter to eliminate the false triggering of the protection. Now if it is greater than 7 volt, then you must turn off the switch. That is one of the same protection algorithm is implemented in Skyper 32. This is easily implementable, but the thing is that it is parameter dependent. When temperature change, there must be maybe all the parameter get changed, and it may be false triggered. So this is not too much smart. So now if you implement a shunt across this bus, you can sense the shunt voltage. That is the more accurate one, because shunt voltage is not at all temperature, not too much temperature dependent. It is quite linear across our operating temperature up to a 150 degree. But again, implementing a shunt and this filter and all these things, there is additional circuitry required, and that is increase your system cost. So all depend on, but that was intelligently you can monitor how much current is transferring to the load or transferring through the device. Based on that, you can take the decision. Those are the smarter way to protect the device during a turn on condition. Now, when you turned off, this ringing appear parasitic ringing. Now, one way to damp this parasitic ringing is to use an RC snubber. But when you connect the RC snubber, which is the old way, but all RC snubber is dissipative snubber. You need to you need to have a separate evacuation, heat evacuation or heat management system to, or it also takes some lot of space to what's your PCB or whatever system you want to design. But also this snubber is not too much effective because of excessive heat across the resistance may blow up. Now to avoid that, there is called active clamping or advanced active clamping. In active clamping, what happens is that when you turn off the MOSFET, you sensing the MOSFET voltage through a Zener or TVS diode. Now when TVS diode, when the voltage is reached to a certain value, the TVS diode got breakdown, and across the ACL pin or clamping pin, you can sense some voltage. Now, when you sense some voltage, you can turn on the MOSFET in the linear region instead of saturation region. So when you do so, the overshoot voltage across the MOSFET try to flow through the same MOSFET, but not in the switching region. It is on, you can slowly turn on the MOSFET just around the threshold, not going towards the play to or not hard turn on. So now when you do so, you can see there is some, instead of this ringing, the voltage is clamped. This clamped is, you can tune how much voltage you want to clamp through this clamping diode or this T-phase diode. So no losses number, no extra component is required. You are using this phenomena of driving the MOSFET. You are using that phenomena, or you are using the same system to damp the excess energy and passing through the MOSFET. Okay. Now all this thing, we are damping or absorbing the energy. Actually, we are dissipating the energy. We are not using the energy. We are just dissipating somehow. So now to avoid that, the soft switching is very much required. To in soft switching, we are using this parasitic energy to charge up the capacitor or the output capacitor. And when the capacitor is charged, then the body diode of the MOSFET try to conduct. When body diode of the MOSFET is conducting, then we can turn on the switch. Now, when your body diode is conducting, so voltage across the switch is 0 because body diode is already conducting. So now, if you turn on the switch at 0, when voltage across the switch is 0, then the switching loss is minimized, or theoretically it should be 0, but in practical scenario, their switching loss is minimized. Now, also when switching loss is minimized, your bus overshoot, which I showed you here, this kind of overshoot is become 0, because all this overshoot, you are absorbing this energy, you are using this energy to charge the body capacitance. I will show you some experimental waveform. So now this is the basic concept of soft switching. So most popular soft switching converter is that LLC converter. So here there is one L. Okay. Sorry. Yes, there is a resonating LR, LM, and CR. So one is resonating inductor and resonating capacitor, and LM is the magnetizing inductance. So immediate by virtue of this converter, by the principle of this converter, you can have a GVS, zero voltage switching, at the primary side, and at the secondary side you can have, since it is a pulse, it is a sine wave, so, or a high frequency sine wave. So at the secondary side you can have GCS automatically, because if you, as you have the sine wave, so sine wave must touch the zero at the zero crossing point. So the secondary side switch have automatic zero current switching. So at the secondary side also you don't have any oscillation. So at the primary side is also clean and secondary side is also clean. Now when you say about the oscillation, primary side oscillation, secondary side oscillation, those oscillation actually create radiated EMI and conducted EMI. So when you use this kind of LLC or resonant converter, so those these soft switching phenomena also reduce the EMI EMC performance, or intensity of the EMI EMC. It can enhance the EMI EMC performance and reduce the filter size, EMI EMC filter. The filter requirement, filter design for the EMI EMC, that is called EMI filter. The filter requirement is very low since everything is clean. Okay, so this is the basic LLC converter, where primary side is full bridge, and the voltage across the bridge is either plus 1 and -1. That means since it's a full bridge, so the output of the bridge is plus Vin and minus Vin. So when you pass this bipolar voltage through a resonating element, and if you sync the this switching frequency or the switching pulse with the resonating frequency, which is 1/2 pi root LC. Now when you do so, then you can see the resonating phenomena. That means during the turn on time, the resonating current will flow. So when during the positive half cycle, also your current, positive half cycle of the voltage, your current will also positive half cycle of the sinusoid. When negative half cycle appear, the current will also negative half cycle. So by that way, due to positive and negative half cycle, this current is a positive. If you combine the current, this is a positive half and negative half, that is full sinusoid you can get at the resonant frequency. Now this is the transformer for isolated for isolation. So when this resonating current flowing from the primary side, it also flow to the secondary side. This induced current at the primary, it will flow through the secondary. So now when it flow through the secondary diode bridge, you can rectify this secondary current and dump the current to the capacitor. So this is kind of current fed converter at the secondary side, because you are feeding the resonant current to the capacitor. So there is no extra inductance is required, like forward converter or push-pull converter. There is one resonant one current fed inductor. By this resonating inductor, you are creating a current waveform. So that inductor is also creating a resonance, also creating a current source. So that current waveform, you can, if the current, that current source, you can dump to the output capacitor, and from there you can take to the load, take towards the load. Okay, but problem, everything is fine. Problem is that the load regulation or is very difficult to control actually. Apart from the resonant, the output voltage is completely depend on the load resistance, and the gain curve is not too much wide compared to other converter. In other converter, the output voltage to input voltage ratio is which is the converter gain, like B out equal to D into V in. So here the D can vary from 0 to 1 in wide range. But in this case, the output transfer function is not, the gain is not too wide. You cannot operate at very high frequency. These are the limitation of this converter. So instead of this full bridge, primary side full bridge, for low power application, we can use that half bridge. Just we replace the full bridge full bridge network with half bridge, and this same resonant tank is connected between the pole and the ground of the bridge. So here you can have half gain, because you are now swinging from 0 to V in, but in previous case your swing is plus V in to minus V in. So as your voltage swing getting half, so overall your gain is half compared to the other. Now the problem is here, if you see the input current, when it is turned on, the current is conducting. If you see the input current, the current is going to make a half sinusoid. But when it is 0, the current is not at all conducting here. So if you see the source current, you will see a pulsating current, some sinusoid, then a blank, then a sinusoid, then a blank. But in case of previous half bridge, full bridge converter, because diagonal switch are conducting, so you can see pulse, then pulse, then pulse. Means the current is continuous, not like not continuous, pulsating frequency. So the average value of the current is very middle or the √2 times of the peak, a constant value. But here, because of the discontinuity of the current, you need to have a higher filter or higher capacitor, so that during this blanking time, the capacitor can feed the blanking current. Now to avoid that, we can switch to, that is called asymmetric LLC. Now we can switch to symmetric LLC, where this instead of connecting to the 0, instead of connecting to the ground, the LC network is connected to a splitted capacitor. This capacitor, you can use a resonant capacitor as well, where there is only one inductor. You can eliminate this CS, and you can split this CS between C1 and C2 by Cs by 2, Cs by 2. So if you do this thing, then what happens is that the current is no longer blank, one blank period. Instead of that, there is a continuous pulse of current. These two are very popular topology in the industry, especially in the telecom power supply. So I have almost 5 years of experience in designing telecom power supply. Telecom power supply is very much noise sensitive because this power supply noise is affecting the telephone line or the communication line. So they are very much fond of this soft switch converter. Okay, so now yes. Okay, now if you want to do the modeling of the LLC converter, you can see this this switching network. You can either you can model with a function which is S of t, where this S of t varying between the plus and minus and multiply by the voltage, this DC voltage. Now when it is S1 and S2 is on, that means this diagonal switch is on. You can see across the bridge, you can see the plus voltage. Now when this diagonal switch is on, across the bridge, you can see the negative voltage. So there is a plus minus pulse you can see across the V bridge. So now when you pass through this tank, you simplify this tank with C, L and C, and this is LM. So if you pass through the tank, so one resonating current is flowing through this network. Now this resonating current is also flowing through this is a reflected load from secondary to primary. So this resonating current is flowing to the load. So your load is actually consuming the resonating current. Now this LM current or magnetizing current, the current flowing through the LM, is not contributing to the resonance. But if you see the current division, you can see one current is the tank current, which is coming from the bridge. This bridge current is splitted into two parts. One is going to the load, which is active current. Another is coming back to the source through a LM or the magnetizing inductance. Now this current is reactive current. Now this reactive current is flowing through all your parasitic element, because this current is returning current. So this resonating current is a filter version of the current of the tank current, which is going towards the load, and all the unfiltered version or all this junk current, you may say, is flowing back to the source. Now when it flowing back to the source, it flowing back to the bridge, so it is coming back from this path because here transformer is connected. Now when coming back to the bridge, it charge the output capacitor of the switch. Now when it charge the output capacitor, then when output capacitor gets charged, then bodied out start to conduct, because the bodied out get forward biased. Now when bodied out start to conduct, the voltage across the MOSFET is getting 0. Now at that time, you need to turn on the MOSFET. Okay, I will show you what will happen if you do so. Now this is the tank gain of the tank. You see there is only the tank component. There is no other reactive component or any kind of element. So the depend on the tank gain of the tank, the load will see the voltage. So you can see the tank gain is also depend on the quality factor or the reflected load. That is why it is very much difficult to regulate this converter. That is why this converter cannot be used as single stage one, because PFs, the voltage or this driving voltage is derived from a PFC or a boost converter as a pre-regulator, which can hold up the this DC bus. So you can see the it is not depend if your B in also B in get change, this curve will also get changed. That is why, but because of this digital control nowadays, it is easy to control, but uh, overall it need cycle by cycle control and all these things. Very fast control is very difficult to implement here. So it is a very slow system. Okay, so now this return current or magnetizing current, you can see this current is flowing back to the switch. So now here, so here is this is the switch current. So here I turn on the switch, here I turn on the switch. But see, instead of 0, means instead of starting from here, the tank current is shifted by some angle. So now when I turn on the switch, the current across the switch is no longer 0. You see there is negative current. Similarly, if you cut this version, you can see here there is a negative current. Now this negative current indicate that the current flowing towards the device, because when the this is a conventional this is a sign convention of the current is that when any current coming out of the device is positive, any current going towards the device is negative. Now when this amount of negative current is going towards the device, now it will charge the capacitor. Now if you charge the capacitor, this current, now when you turn on the MOSFET here, so this current charge up the capacitor and it creates the 0 voltage switching. So now you have to optimize how much current you want to push back to the switch, how much current you need to create the GVS. This is completely depend on the device rating, how much is the output capacitance. For GAN, it's a very much for GAN device, this capacitance is very low and quite linear. But for MOSFET, this device output capacitance quite high compared to, very much high compared to the GAN device. So you need a big amount of current during the short time to charge this capacitor. Now this current is coming from the LM. So when you use the GAN device, your LM must be high. This is a reactive loss. It reduces the efficiency of the converter, but it can enhance. It can reduce the efficiency in one term, but it can enhance the efficiency in terms of the switching loss. It can reduce the efficiency in terms of reactive circulation, but it can enhance the efficiency in terms of the switching loss.
Follow for the next story. This is how Nokia killed itself. Nokia ruled India. This is how Dunzo killed itself. By 20.
Okay. Thank you for mute. So this is the actual. Okay. This is the real hardware waveform. So you see the voltage when you this is the VDS or V bridge. You can see the voltage is not going from 0 to the bus voltage immediately or abruptly. So the voltage is around 300 volt and this is 0 volt. Yes. Now you can see the voltage is 300 volt and see this is 0 volt. Now see when it is this transition from 0 to 300 happen, it is not like fast. Not so dVdt here is not like immediate. It is not like from 0 to 300 immediately. So you can see it is going slowly and go up to and follow a parabolic nature, because the output capacitance of the MOSFET is non-linear. It is not linear in nature. As it is non-linear, so capacitance varies when the voltage across the device is changed, depend on the voltage across the device. So when voltage is high, the capacitance is very low. So you can see here is slowly going and immediately it gets charged here. So here you can see here the GVS energy is lost. So that is why a small ringing happen. But if you tuned it correctly, this ringing will no longer exist. But you can see at the during turn off, the turn off energy is very smooth. You can see. So this is the main advantage of LLC. See, this is the resonant current flowing towards the secondary. You can see at the secondary there is a complete sinusoid, but at the primary you can see a broken sinusoid. Why it is broken? Because there is a resonant current plus inductor, the LM current. And if you see the voltage across the resonating capacitor, it is 90 degree out of the phase of the current, because current and current voltage through the capacitor is 90 degree opposite to the current. Now if you zoom this transition, you can see this is the negative current. If you can measure this negative current, how much negative current is required to charge the output of the capacitor. So this negative current is flowing through the device and create this smooth, you can see there is smooth transition, not abrupt transition from 0 to 300 volt. This smooth transition create the GVS. That is the effect of GVS. Okay, now if I remove the load, you see the load current is 0. This orange one is 0. Still I have a smooth transition from 0 to 300 volt because of this magnetizing current, which is flowing back. I am taking back the current from the source and feed it back to the bridge. So you can see how much current, around 2 amp to 4 amp peak to peak, 2 amp up, 2 amp down. So that is 4 amp peak to peak current is flowing through the switch. Okay. So now if I reduce the load and reduce the voltage also, okay, now you can see there is my GVS energy start to charge the capacitor here, but energy is finished here. My current is finished here. What is the scenario of this? When my LM current is not too much sufficient, or my reactive current is not sufficient to charge the energy. So at that scenario, it try to go for to charge the output capacitance, but I turn on the switch or my dead time is very low. I did not allow sufficient time to charge the capacitor. So in these two scenario, you see there is the start to follow the to charge the switch and try to have the GVS, but their energy is lost. That is called quasi GVS scenario. Now, how much GVS you want, that is also depend on the designer. Now you can see if I don't take any current from the source and don't circulate any reactive current, you see all the current is 0. You can see the abrupt change in the switching transition from 0 to the peak voltage. Generally, when you design the converter, you may experience this kind of ringing. So to avoid this ringing, you must introduce a GVS cell to feedback the current to charge the capacitance. Okay. Thank you very much. If you have any question, you may please ask.
Hello. Dear participants, please. You can write in chat box also. Any query, please, from audience side? Okay.
Sir, can I ask
Okay.
one question? Good evening.
Yes, yes.
Yes, please.
Sir, for high power, high voltage, like more than 500 volts for charger, do we need to use IGBT rather than MOSFET? Is it correct?
There is no hard and fast rule.
Okay.
What is your operating frequency?
Frequency is 50 hertz.
Your switching frequency is 50 hertz.
No, not switching. Supply frequency is 50 hertz. Which supply I want to convert from AC to DC, suppose.
But what is your switching frequency?
I'm not recollecting, sir. At this.
If it is below 20 kilohertz, you can use IGBT. But
Okay.
you know, at high 500 volt is not considered as a high voltage.
Okay.
If your bus voltage is around 600 or something, you can use IGBT, those block IGBT, all these things.
Okay.
But to start with, you can use IGBT because MOSFET is very sensitive. If you cannot drive MOSFET very efficiently, it's very delicate things. Immediately MOSFET can blow, but IGBT can withstand. Also, the protection of IGBT is very well known.
Okay. Thank you, sir. Thank you for clarification. Thank you.
Yeah,
The switching frequency is that how long you have to put on the device?
That is very much. I'm very much sorry to say that is very false concept or vague concept of switching frequency. The concept of switching frequency, that how fast the transition happen from 0 to 1. That transition is actually control everything, not your steady state point. Your steady state timing is not that much important. Your switching frequency high means your transition and all these things should be fast enough. Are you getting, Mr. Vivek Kumar?
Yes, no, for that person I have replied because he don't contact that things. That transition period, I know that is the required for the MOSFET and IGBT. Because
that,
there have a capacitance effect will be turn on, lie down. Whatever
Turn
the
on and turn off time is very.
yeah is an important one.
Mm.
Yeah.
When we describe the switching frequency, we need to consider this how much turn on and how much turn off, because from a square wave pulse, if you eliminate those two transition, then your square wave pulse is just like a DC pulse, right?
Yeah, right.
Good explanation of GVS. Yes, thank you very much. I am working on GVS almost last 2 years, different topology to implement GVS. In industry, GVS is the only things implement in the converter. It is very important phenomena. I encourage all of you to do experiment or do hardware in LLC. It is very much simple to implement. So I encourage all of you to see what the phenomena going on. It is very much very. Power electronics is like that actually. When you don't do the things experimentally, you cannot understand with the bookish knowledge. So LLC converter is very much easy to implement. It looks difficult, but is very easy. All the parasitic is taken care by the switch.
Yeah, right. You are saying right, sir, because I have done the MTech in power electronics in 2000, sir. So nowadays very changes. I have done the MTech in 2000. Now it's a fully changed.
Yes. Can we?
Or any other question, please? No, actually, Dhiman,
Yes.
one question in chat box. Can we use LLC for grid integrated system?
Is completely depend.
Or boost is the better option?
What do you mean that? It's completely depend on which power stage you are using. Yes, LLC you can use for DC to DC conversion as well as DC to AC conversion also. But okay, for micro inverter they are using LLC at DC to AC conversion, and AC to AC conversion they are using matrix converter at the next stage. So it depends on which power stage you are using the LLC. You can use the LLC. LLC is very nice converter. You can use it different scenario, different condition, how you design your system. Yeah.
Sir, can I? Sir, excuse me, sir.
Sorry?
Yes.
Sir, can I use LLC for both solar and diesel for the charging station?
Yes, you can use LLC everywhere. But you need to see what is the range of input voltage, because it cannot operate at wide range, as I show the curve. If your input voltage is almost fixed, you can use anywhere.
Yeah, I think, and if we have grid and solar and a diesel generator, and these three types of inputs we are taking for optimizing electrical vehicle charging.
Yes.
For this, we are using normal that means bidirectional AC to DC converter in my research. So can I replace it this
Bidirectional AC to DC. Okay.
Okay. Can I replace this one LLC circuit?
Yes, you can replace, no problem. But you have to just take in your mind that LLC converter is an AC source, which is resonating current, a current source. Now you have to use that current source directly to current, or you have to convert the current into voltage. That thing you need to take care of. This is LLC is just a current source.
Okay. Yeah, I think I convert the whole voltage source. No?
Sorry?
It is for this converter we are connecting the battery. After the converter, we using to connect the battery.
Yes, for battery charging, LLC is widely used.
Okay. ठीक है.
You
Thank
are
you, sir.
converting a battery, but before battery, you need to dump the capacitor, yeah, the high frequency
Yeah.
current.
Yeah,
Then
yeah.
you connect a battery to pass the low frequency current.
Okay.
Up to how much voltage level LLC can be used? It can.
So my battery range is
How much power voltage level? It depend on your switching device. But in case of HVDC power transmission, they are using mostly multi-level converter because of the too much high voltage. Okay, next.
Sir, one question is that what is the big difference between DAB converter and LLC converter? DAB converter
DAB
and
is actually the working principle is different. DAB is when there is power flow between two source, then DAB is used like high voltage and low voltage. When there is a power exchange between source to source, and you create a phase angle between them, then this is the working principle of DAB. But LLC is working principle, you are creating one sinusoid current, one sine current, and you are feeding this sine current to the load. That is the principle of LLC. But there is also resonating DAB. But DAB is, quite difficult, means quite a different concept. This is a source to source interaction, but LLC is unidirectional. Single LLC.
magnetizing inductance is large in DAB.
It completely depends on your design things, how you're designing the converter, means what is your parameter. But if you see the overall efficiency, it is the same. The magnetizing or reactive current you are saying, that is to feedback the switching to the switching capacitance. That is also same. Whatever you do, LLC, DAB, phase shifted food, whatever converter you do, you need to feed a certain amount of current to achieve GVS.
Yes.
DAB is popular for GVS operation also.
Okay.
But DAB, very difficult to there. Okay, one more thing, DAB is quite regulated compared to LLC.
Okay.
Also, the range is quite wide in DAB, but efficiency point of view, almost same. LLC is better, can achieve better. It completely depend on the parameter and how you optimize the magnetics and all these things.
Thank you, sir.
Professor, good evening.
I'm not professor.
Sorry.
But good evening.
Can this LLC converter can be used for bidirectional charging applications?
Yes, you can, but at the secondary side also you need to connect one LC tank.
Okay, okay.
Then when you feed, then it will be two LC, one LC at the primary and at the secondary. Then again transformer at the secondary side of the transformer. You need to have another LC circuit.
Okay, okay. And controlling is easy in that case?
No, overall LLC control is very difficult. Overall LLC control. There is still, paper. There's still paper is publishing how to enhance the gain and all these things and the control.
Okay.
I have also some patent on tank design, how to achieve wide range again, all these things.
Okay, very good, very good. Thank you.
Thank you.